Hey folks, Dan here. I'm excited to share the first interview on the MicroArch Club podcast. Today I am joined by Philip Freidin. Philip has a great backstory, growing up in Australia and getting involved in electronics, programming, and computer architecture at a young age. He went on to work on a number of well-known products, such as the AM2900 family of bit-slice logic chips and the AM29000 RISC processor line at AMD, before moving to Xilinx to work on FPGAs. We only covered a small fraction of the experience and wisdom that Philip has to offer, so I hope to have him back again in the future. I also should extend a special thank you to Philip for being willing to be the first guest on the podcast, and to Jan Gray for initially connecting us. With that, let's get into the conversation. All right. Well, Philip, welcome to the MicroArch Club podcast, and thank you for being the first guest.
Thank you very much for inviting me. Really looking forward to the discussion.
Absolutely. Well, definitely honored to have you here. I think we had an interesting introduction to one another. I had written a blog post about lookup table RAM, or LUTRAM, and had posted on Twitter, and then we had a mutual connection who mentioned, hey, maybe I should talk to you because of your background in the area, and that might be something we're able to touch on in the interview today. But I always appreciate getting connected to folks like yourself, just kind of randomly or by happenstance like that.
Yeah. You're referring to Jan Gray?
That's correct.
Yeah, I've known him for about 31 years.
Okay.
Yeah. And we met while discussing register files and LUTRAMs and doing CPUs in FPGAs, which has been very much an active hobby for both of us.
Absolutely. I've mostly come into contact with him through, now he leads or co-leads the RISC-V soft CPU special interest group. So I know he's doing some work on that front, but he's definitely someone else who I'd like to have on the podcast in the future, as I'm sure he has some.
Yeah, he's a very smart guy. Certainly worth talking to.
Absolutely.
And, with regard to soft CPUs, we are both pretty much together the pioneers of doing that. And it was actually through him asking some questions and then presenting his ideas that we discovered that almost concurrently we had architected CPUs that looked extremely similar using Xilinx FPGAs. So
that's awesome.
Yeah.
Well, maybe we'll get into that when we get through your story a little bit. Going kind of to the beginning. I know when we were chatting kind of off the air last week, you mentioned that you didn't grow up in the United States, but part of your plan in getting into the industry and that you actually had a plan, right? Was this process of moving to the U.S. So I wonder if you could just take us back to kind of growing up and your education, and then what sort of your plan was to enter the industry.
Yeah. So I grew up in Melbourne, Australia, and I was doing electronics and then computing from an extremely young age. I probably started soldering components around 8 years old with my mother's help, primarily holding a screwdriver over the gas stove and getting it hot enough to melt solder. And then eventually someone bought me a soldering iron. Initially just making things like crystal radios and 1 and 2 transistor radios, that sort of stuff. Along the way, I don't know if you're aware of it, but there's these kits, like 101 projects that Radio Shack and other companies made. And Philips, which you've probably heard of, also used to make such kits. And so someone got me a Philips Electronic Engineer number 8 kit. And so, my earliest sort of transistor constructions was using that kit. And, it's the Philips kits probably weren't that prolific here in the US because it really primarily existed in Europe, and Australia was probably more aligned with Europe than the US at the time. So here it would have been Radio Shack kits. Australia, UK, etc., it would have been these kits made by Philips. The lasting memory is that they used these really strong springs, and for someone aged 8 or 9 years old, it really hurt my fingers putting it. So basically, whereas the American kits had these fairly floppy cylindrical springs, you just push over the side and you could slide something in. The Philips kits were built on a sheet of masonite with a 1 inch by 1 inch grid of holes, and you pushed a pin from the underside which couldn't go all the way through, and then you pushed this very strong cylindrical pin from above, and then if you pushed it down really hard, you'd have an exposed loop. You'd put your wires in, then the spring would then come up and hold it. But getting those springs in place and pulling them off when you finished a project and wanted to do something different, I mean, it didn't quite bring your fingers to bleeding, but it was close. So that's what I remember most about the kit. The school I went to, so we're sort of jumping forward from that by about 4 years, so around age 12. The school I was going to, there was a maths teacher who got a computer, what's the right word? Timeshare computer terminal. So we're talking 1972. That dates me a little bit. Of course, this probably does it as well. So around 1972, the school got a computer terminal, and back in those days, computer terminals were something called an ASR33, which is also called a teletype. So it transmits and receives at 10 or 11 characters a second, and the mass storage available is called paper tape. Right? And so you would, with the ASR33 terminal not connected to the computer, so you're not paying for services, you would type in your program and punch out a paper tape, and then when you'd finish creating your program, you'd then use a phone to dial in to the computer. So this is a little bit like bulletin boards of 20 years ago in terms of dial-up type stuff, except the data rate was 110 baud. The modem was the size of a PC mini tower case.
Okay.
Right, and all it did was 110 baud.
Right.
And so what you do is you'd quickly go through the login process, turn the paper tape reader on, and read in the tape that you'd typed. So it was, banging away at 10 characters a second, right? And as soon as it finished reading the tape, you'd type run. The program would run for some amount of time, or it would loop forever or whatever, and it would print out results at 10 characters a second. Right. And then, unless there was a good reason, you would then disconnect from the service. So it was, how short a time can you stay connected? And the way services back then were measured and charged was with a unit you've never heard of before called a Kilocore Tick. Kilo is the amount of memory that your program was using in kilobytes. So like 5 kilobytes or 10 kilobytes.
Right.
Core was in core memory, and a tick was a second. So if you used 10K of memory for 50 seconds, you'd be charged 50 Kilocore Ticks. Right?
Common currency there. Everyone's walking around with some Kilocore Ticks in their pocket.
Right. So anyway,
what kind of what kind of operations were you doing on the computer at that time?
So it was mostly math problems. So, this is, let's see, I'm in approximately, this would have been 8th grade.
Okay.
In Australia, that's called Form 2. So the naming of the stuff in it is quite different in Australia from here. In Australia, it's primary school 1 through 6, and then secondary school is Form 1 through to Form 6. So it's still
Gotcha.
12 years of schooling, but for secondary school, it's just Form 1, 2, 3, 4, 5, and 6. So it would have been Form 2. So, we're doing some calculus type stuff, some linear programming type stuff. So, simple algebra, some things like finding minima of functions, that sort of thing. And, maybe writing some computer games as well. But
Right.
because of the budget, which was for the whole school, you really couldn't get too carried away with what you were doing with this one terminal shared across probably 60 or 70 students, although most of them weren't into it. But there was a small group of us who were. For me, I needed much more, and so it turns out, so the service was provided initially by General Electric, and then it was by Honeywell. So the computer was actually a General Electric 235.
Okay.
Some just called just GE 235, but they sold that division to Honeywell, and so it started off being GE timeshare, then it became Honeywell timeshare. The computer center was located in central Melbourne, and that for me was a half-hour trip on public transport. And so after school, one day, I headed into the city and found the GE building and went in there. And I'm like a 12-year-old, right?
Right.
And I surprisingly know something about this service. I came up to
Right.
the reception desk and I said, "I've been using your service, but I really want to see the computer that we're connected to. Right? Is there some way I can get to see it?" And the receptionist, when I came in, she was chatting with what turned out to be one of the computer system technicians.
Okay.
And so she handed me off to the technician. And whether because he was interested in helping me or maybe to impress the receptionist, either of which is possible, he took me in the elevator up to the computer center. And there was a big glass window where you could look in at all these machines and the people in with white coats loading and unloading listings from the line printer, mag tapes. There would have been disk packs, but they wouldn't have been particularly much storage. Like back in those days, a disk drive would be a pack that was maybe 14 inches in diameter and maybe 6 to 8 inches high, and that might be 20 megabytes.
Wow.
Right? And that's removable. This is removable media.
Right.
Right. So there was a plastic cake tin, as I refer to it, over the top and a cover at the bottom. And there was a way to hold the handle in the top, rotate a latch on the underside, which would remove the bottom. You then place it into the disk drive, which looked like a washing machine. Right. And then again, an appropriate twist of the wrist locked the pack into the drive, and you took the cake tin off. And then the heads then came in from the side to access 20 megabytes of data, right? I mean, I have text files that are 1,000 times the size of that now.
Right.
So anyway, big glass window to show me, there's the computer, and he pointed to different things and told me what they were, and I asked appropriately intelligent questions, and he said, so then it turns out that as someone who actually did maintenance on the machine, he had an unlimited account. Right? No Kilocore Tick limits for him.
Right. I bet you were excited to hear this at 12 years old.
Yeah, it was like, wow. So it turns out Honeywell Timeshare had a training room with 10 teletypes and a desk and a big blackboard at the front. And so they did training for corporate customers. And he said, let me set you up with some stuff you probably can't do from the school terminal. And it was some game programs, right? Nothing particularly exciting. And, it's still at 10 characters a second, right?
Right.
So he left me there, to play for, I don't know, half an hour or so. And when he came back, I said, I've played enough, right? How do I get to really learn more about, using it? And he said, well, for our corporate customers, we have training programs, right? And so instead of just programming in BASIC, you could, if you want to spend the time, learn Fortran and Algol. And I was all for it. And so that started what was probably 6 months of me going into Honeywell Timeshare.
Wow.
3 or 4 nights a week and getting there usually around 4 or 5 p.m. and staying till about 10 p.m. And as I said, I did it for about 6 months until my parents blew the whistle on me because my school grades had fallen off a cliff. But I was now writing 300 or 400 line Fortran and Algol programs at age 12. Oh, and BASIC as well, right? So basically Honeywell Timeshare technician, I don't know his name, I don't know how I would ever thank him, but he gave me a resource that no other 12-year-old in Australia would have had.
Right.
It was just phenomenal. And so there I am, and I've already learnt the only language I didn't learn because that machine didn't have it was COBOL.
Okay.
Right? Oh, and assembler. So I hadn't yet done assembler.
What instruction set architecture was that machine?
I do not know.
I'll look it up and put it in the show notes. Yeah,
it's almost certainly does get a reference in Wikipedia.
Okay.
And there were several machines. It was GE 215, 235, and 245, and the machine we had was a 235. And these machines were 19-inch cabinets, maybe 16 to 20 of them in a row, where something like 4K of memory was a 19-inch rack, 6 foot high, 3 foot deep, and 25 inches wide or whatever that a 19-inch rack is by the time you put the wrapper on it, right? So anyway, so that was my introduction to programming, and learning multiple languages and getting already to do some comparative type stuff. The damage that did to my educational path was pretty severe and lasted me through till the end of school, because there was a lot of stuff that I just didn't learn, because on the other hand, what I did learn has lasted me a lifetime.
Right.
Right? But, for instance, I'd be lost without a spell checker.
Right.
Right?
Well,
because that was one of the things that went by the wayside.
Right. Well, that's so interesting. A lot of ways, it's a more physical or real world example of kind of like diving through the abstraction layers, right? You're at the end at this teletype, and you have to kind of like go physically take public transportation to go see the thing. And it's interesting to compare that to experiences today. One of the things with this podcast, for example, I'm trying to do is kind of like pull back some of those abstraction layers and see what happens in the machine. But for me, a lot of times that looks like, going to YouTube and watching an interview or listening to another podcast.
Sure. Well, or listening to a greybeard on YouTube telling you this type of story.
Right.
Yeah, and I didn't mention that, of course, that technician, got me the appropriate credentials No idea how, to let me not have to look for him every evening when I came in to play on the system. But basically, no one in management either knew about it or cared about it. But it was just a wonderful learning experience for me.
That's awesome.
Yeah. So after that, a few years later, so around 1974, I started playing with, playing and some work on a PDP-8. So the DEC computers really dominated my early hands-on computing. So there was how did this happen? So I was working as a summer job. So in Australia, the end of the school year is, end of November, and then we have like 8 to 10 weeks off, which is end of school year and Christmas, and it's the middle of summer in Australia. And so we can get pretty long summer jobs, right?
Right.
Significantly longer than what you can get here in the US. And so I got a summer job working in the electronics department of a hospital, right? And this was arranged by my father, who was the head surgeon at that hospital, right? And he put a nice word into the head of the electronics department. And so I don't know if they do it now, but at least back in those days, hospitals had, as I said, a electronics department with maybe 4 or 5 electronic engineers, and primarily they were doing equipment repair, right? But they also had they did some design work, because the hospital, the large hospitals, and this was a large hospital, tended to be linked to a university. And so you'd have university doctors who taught at the university, practiced at the hospital, and might be doing some research. And if that research needed special instrumentation, then the hospital had an electronics department who often, helped along, right? So I got this 10-week or so Christmas holiday job, and the head of the department, had me primarily doing, go pick up this ECG machine on the 8th floor of the hospital and bring it back for repair, or go see if they forgot to plug it in. Right. There was always these jokes of nurses, failing to plug in something, or getting terminals round the wrong way. Once had, it was some piece of equipment that was somewhat portable in a box, about that big by that big. Whoops, right? And someone said, disinfect it. And, what they probably meant was, get some appropriate cleaning agent and wipe down the front panel and whatever. Right. They put it into a bucket of disinfectant. Right. So, so sometimes, some things will be beyond repair. Anyway, because they had design capability, the head of the department said, as well as doing this repair stuff, and they had me doing, once I'd actually shown that I understood what was going on, I was actually doing repair of equipment. Some of it was fairly simple, things like broken battery terminals, or wires to a potentiometer, or a frayed terminal to an electrode for an ECG machine. And some of it was simple, but some of it was some bug tracking. He said, we have the parts, why don't you make a digital clock, right? And back then, it was 7400 series ICs and Nixie tubes. And so I made a 4-digit clock, and he let me just basically, work through the data book and gave me guidance when I asked for it. But as well as the experience of working, in a real engineering department. This is, so now I'm, I guess, around 14. Yeah.
Right.
So I actually got to design a digital clock, and back then you were having to put a lot of components together, right, to actually, build different modulo counters for, 59 rolling over to 00 and, 12 rolling over to 1, that sort of stuff. So I ended up with a digital clock. I ended up with some experience, but as I said, this was a teaching hospital, and one of the departments that I served had a PDP-8 computer, and so I requested ability to use it in the evenings when no one was using it. And the medical researcher knew me not by my correct name, Philip Freidin, but my name was Joe Freidinson, as in my father's name is Joe, and I'm Joe Freidin's son.
Fair enough.
Right?
Fair enough.
And that carried insane creds in that hospital. Right? So I was allowed to play with the PDP-8. Now the PDP-8 is, in this case, was 8K of 12-bit memory. It executed what today we would call pretty much a RISC instruction set, and yet it was from the the PDP-8 family dates back to the mid-1960s and extends through to the end of the 1970s in terms of 6 or 7 different models of machine. And the 8E was probably by far the most prolific mini computer that DEC ever sold. It was priced down around 10 to 12K, and you could run, it had a interpreted language similar to BASIC called Focal, which looks not that different from modem line noise. It's a little bit more readable than APL and a little bit less readable than BASIC. But it ran Focal, and so you'd have, well, actually, let me think. The interpreter was actually 2K words, and so on a 4K PDP-8, which is the smallest configuration, you got 2K words, which was approximately 4K half words, which are 6 bits. And if you don't need lowercase because your teletype only does uppercase, you can pack 2 characters per 12-bit word, and if you put 3 12-bit words together for floating point, so for integer, it was 12-bit integers, so minus 2000 through to plus 2000, 2048, but floating point would be a 12-bit exponent and a 24-bit mantissa. So its range was actually better than IEEE single precision floating point, which is 32 bits split as 8 and 24. So there was 4 more bits of mantissa, and so it actually had better range than IEEE, which didn't exist back then. I mean, that didn't come along for another 15, 20 years. But you had this PDP-8 with only 4K of memory, and it had very good floating point, and you could write programs that fitted into that 2K words of memory, including your program and any array data, right? And the PDP-8s could go up to a maximum of 32K.
Gotcha.
Right.
And the PDP-8 has come up a few times in chatting with folks. And was PDP-8 the machine that Unix was originally written on?
No,
I want to say it was a PDP machine, right? 11. That's right.
Oh, yes, yeah. And by the way, the reason they're all called, so this is what I have read many times and heard from people. The reason DEC called their machines PDPs rather than computers, right? They weren't called computers. They were called programmable data processors. And that was because they were aimed at individuals who might work at a company that had a big computer department that was in charge of buying all computers and keeping them behind big glass-walled rooms with the high priests in their white coats. And so for researchers who wanted to get a computer in their lab, they could order it as a PDP.
Right.
And the computer
Didn't go
department,
through the red tape.
Right. Bypass all the red tape. So, they were also, very prolific in universities because DEC made some large systems. The PDP-10 and the PDP-20 were campus-sized machines that might have 100 terminals connected to them. So the terminals were still these ASR33s, right? These dominated the 70s. They were eventually supplanted by what they called glass teletypes, which we would now refer to as dumb terminals.
Okay.
Right, so 24 lines of 80 characters and a keyboard, and probably, depending on when you did this, there may still be a paper tape reader and punch associated with it.
Gotcha.
Okay, yeah. So anyway, there was a department there that had a PDP-8, and they didn't have anyone to program it. And I said, I can program. And so one of the researchers, who had got the computer for his department, but hadn't managed to get the funding to get a programmer, had me doing programming. And so I was writing simple data acquisition programs, absolute real-time stuff written either in Focal or in Fortran 2. That's a much earlier version of Fortran than... most people who learn Fortran 4 or something more recent, but there was an earlier version called Fortran 2 that was sufficient for what we were doing. And so this was programming on the PDP-8, still everything with paper tapes, but now with a Fortran compiler, and that meant the Fortran compiler was on a paper tape. So you'd load the Fortran compiler from a paper tape, then load your program, and it would then read it in, and you'd read in the paper tape several times, because it would first of all build a symbol table, then read again, right? And so, compiling might take 2 or 3 hours of feeding first of all the Fortran compiler in, then loading the linker, and then loading the libraries, and then loading the intermediate binary, and then at the very end of 3 or 4 hours, right, you'd get a new paper tape, which is a binary version of what was your Fortran program. Right.
And were you like the linker and the libraries, you're manually loading these into the machine, or yeah. So it's interesting. That's like steps we still take today, right? To compile and link a program, but you're physically participating in the process.
Right. In fact, so for the Fortran compiler, it was like a 2 or 3 pass compiler, and so you'd load. So the first paper tape you'd load would be Fortran compiler pass 1, and then put in your paper tape. It would build a symbol table in memory. You would then load in Fortran compiler pass 2, which would overwrite pass 1, but it would now have the data left over from pass 1. Then you read in your program source a second time, right? And now it's starting to build the, I guess it's the data structures and the code tree, and figuring out branch distances and that sort of stuff. And then there was a third pass. The third pass output was the one that took whatever the data structures had been built and then turned it into relocatable binary. Right? So now you've got a relocatable binary version of your program, but no libraries, right, yet. And then you load the linker, And then you might, if you wrote your program in multiple modules, you'd have a relocatable binary paper tape for each one.
Mm-hmm.
And so you'd load in the linker program, then you'd load in all of your things. It would then link between them for where symbols matched between your different modules. Right. And then it would see, here's the list I don't yet know, and it would then tell you which library tapes it needed to merge into your program, right? So things like the floating point library, the sign and cos library, that sort of thing.
Right. And would
then
you,
at the end,
would it be it would do all of that and compile a statically compiled binary? There's no like runtime dependencies?
Yeah, and it was a bare metal thing. There's no operating system in this environment. So yeah, in the paper tape version of this stuff, there's no operating system.
Gotcha.
Okay. At some point, you can add mass storage, like DEC's primary thing was a tape drive that had a 1-inch wide or 3/4 inch wide tape called DECtape, DECtape, and it was a randomly accessed tape that was pre-formatted into blocks, and so there was an operating system at the beginning of the tape, and you could have multiple files, and the BASIC compiler and the Fortran compiler lived on tape, and so all of that paper tape stuff went away, right? If you could afford to buy that operating system and have the mag tape drives,
right?
So a lot of tapes spinning around, right? These are on little hubs that are only about 4.5-5 inches in diameter, right?
Okay.
And the tape just goes off a reel, over the head, and down onto the other reel.
Right.
So anyway, I managed to talk the researcher that I was doing work for into finding the money to let me design a floppy disk drive system. And so this was my first big hardware design. And that was to design a board to plug into the PDP-8 that could talk to a disk drive. And the disk drive was from Memorex. It used 8-inch floppies and could hold about 1/4 megabyte.
And what was the interface that you'd be plugging into on the PDP-8?
Okay, so the PDP-8 has a backplane called OMNIBUS, and actually probably in terms of a sea change in how computers were built, I believe the PDP-8 was the first bus-based computer.
Okay.
Where any slot in the backplane could take any card. Everything prior to that, every place that you plugged a card in, there was only one card that went into that position. Right? But the PDP-8 used these boards that are, I don't know, about 10 inches wide and 8 inches high, and there'd be a single board was the clock, another one was the registers, another one was the ALU. 3 of them together was 4K of memory. The middle board was the actual core plane, and then one of the boards was the read-write amplifiers, and the other one was the bus interface.
Gotcha.
But the bus interface basically ticked away at 1.2 or 1.4 microseconds. The model I'm talking about is the PDP-8E.
Okay.
Right. And it ticks away at about 1.2 or 1.4 microseconds per instruction. Typical instructions took 3 clock cycles, so around 4 or 5 microseconds per instruction, so 200 operations per second, 200K operations a second. And so, it's 12 bits of address, 12 bits of data, and a bunch of timing signals that tell you whether you're doing reads or writes, etc.
Right.
And so not only did I have to design the board, I had to write the device driver, and then I had to get the operating system onto the floppy for the very first time. and the operating system was distributed as about 20 paper tapes. So so now instead of using the Fortran compiler, I'm now using the assembler, right? And the assembler had a similar multiple passes to do an assembly and a linking process to end up with basically the binary version of my device driver, right? And so the operating system was called OS 8, and there are characteristics of OS 8 that you will still see today in the DOS boxes on a Windows 11 PC, right? The syntax on that command line, it all goes back to OS 8. So everything in, OS 8, when you get to the PDP-11s, it was something called RT11. When you get into PCs, it was called DOS, MS-DOS, right? That they all use the same basic command line syntax, and that still exists today in the DOS box or the command box that you see on your latest Windows computers. Right? I mean, there's differences, but it's basically looks very, very similar.
Right. So you were working on this disk drive, right? And go ahead.
Right, and then I had to load the operating system, and DEC built the operating system to be distributed as paper tapes, knowing that some people would have their own device drivers rather than DECs. And so there was a build phase for the OS 8 operating system where you aren't actually running the operating system, you're running a program called build, and you're telling it which devices you want, right, and which services you want OS 8 to provide, and you get to build a custom image of the operating system. And the very last stage is you discover if the device driver you wrote actually works, right, which is when it now has to write it to the media.
Right.
And if that fails, of course, it's back to the assembler, right, to figure out what went wrong. So, but all these machines all had front panels with toggle switches and LEDs, right? And you might want to insert an image. There's lots of PDP-8 images available on the web that you could insert a pop-up of, right? So, basically, you can single step through a program, examine any memory location, change the value of any memory location, all from the front panel. So, you can certainly just load the device driver, right, and then create a little 5-line program that calls it and tells it to transfer 128 bytes from this place in memory to that place on disk, right?
Right.
So anyway, this is me, aged 14, writing operating system device drivers and then building operating systems.
Right.
Right. And so this was now my path up sort of through the really getting into the lower levels, not just of, writing assembler code, but of understanding operating system principles. Right. And again, this was that there weren't any other kids around that were doing the same stuff as what I was doing.
Right. I can imagine it was fairly unique.
Yeah. Again, a great education. I would say the manuals that Digital Equipment made available for the PDP-8 and then later for the PDP-11, they had some introductory programming books that started at the very low levels of assembler that were absolutely excellent, right? For someone who had no detailed knowledge or, university training, their books, which they're all available on bit savers, right? It's kind of historical and, not really relevant, but if you want to have a read, there's a book that came out in 1969 called Introduction to Programming by Digital Equipment for the PDP-8. And it takes you through assembler and explains, they didn't call them pointers back then, but indirect addresses and memory references and a superb coverage of 2's complement arithmetic and just understanding at the very lowest level. You mentioned about sort of levels of abstraction. This has been very much something that I've always thought a lot about from back in those days, because already I could see it. And the model that a lot of people use is they call it the onion model. Right. It's layers upon layers, and I've strongly held that the quality of the work that you do at a given level of abstraction is improved by understanding the level below that you're not using, and maybe the level above that is you're providing a service to. Right.
Yeah. So I heard a quote pretty recently that, when programming, a lot of times we try to be very respectful of the abstraction boundaries on either side, right? Because that's what allows things to interface well together. But from the programmer perspective, right, it's our job to actually venture across those boundaries to understand them, to understand what happens when we interface with them. So I think that's a key thing. Absolutely.
In fact, really, there are two things that come from understanding the level below that you're working. So if you're, let's say you're writing a C program or a BASIC program. Well, actually, C and BASIC are different enough, right? Because C gets compiled to assembler.
Right.
BASIC is, at least traditionally, is interpreted. So there's another layer for BASIC that doesn't exist. Well, it's a different layer. For C, it's the compiler. For BASIC, it's the interpreter. But then eventually you're executing assembler to implement the desired effect.
Right.
The better you understand that layer below, whether it's BASIC or C, that is the assembler level, the better you write your code, right? When you're writing C code, if you know how it's likely to be compiled, right, there's a reason that you might write A equals B left shift 1 as opposed to A equals B plus B or A equals B times B. I mean, they all achieve the same thing, but if you don't have a lot of optimization going on, the A equals B left shift 1 is by far the fastest.
Right.
Unless the machine happens to not optimize the execution time for that.
Right. In my experience, the that kind of like understanding, let's say this is not always the quality, right? There's many things that impact performance at the physical level, but the number of instructions, right, that you're going to be translated to, that's kind of like the first level of understanding maybe how higher level code you write is going to be running. But then even beyond that, right, understanding, and it varies in complexity across different instruction sets, but what's the performance impact of executing a given instruction, right? And that goes into how the processor is designed and that sort of thing. And it seems like you ventured down kind of, you kept going into that level of understanding that. What was kind of like the impetus? Was it just continuing to peel back the layers of the onion?
Absolutely. Well, I mean, designing a disk controller with having never done a tough design, and back then there weren't disk controller chips, right? It was, probably 60 or 70 TTL chips.
Right.
Connecting. Right. So I had to learn bus timing and, how the machine executed instructions. And, that was the other thing. DEC provided full service manuals for these machines and detailed schematics and theory of operation. And so it was expected that some percentage of customers would do all the maintenance of their computers down to the chip level.
Wow.
Right. And so whereas IBM kind of did the exact opposite, right? You couldn't buy an IBM, you had to lease it, and they sent out service people, right, who maintained them. And that was true for most of the mainframe companies. For DEC and then the other similar companies, Data General and Naked Mini and a few others, they all provided enough service information that a competent EE could actually maintain these machines. So I actually did repair work on the PDP-8 as well.
Okay.
And so that meant I was getting into, the partitioning of the computer into different sections and actually, like, hey, it doesn't add correctly anymore, right? And the way you would nail it as that specific thing is DEC made diagnostic programs on paper tape, right? And you would load them into memory, and if memory worked, the program would then run and maybe indicate, hey, I'm trying to do this operation and it doesn't work. And then what you could do is you could write little 5 or 10 line programs and button them in from the front panel after you hand assemble them, and then exercise a specific instruction and say, okay, I've got this operand here and this one here, and it's doing this instruction, and the result is wrong, right?
Right.
And you stick that in a loop, and then you go in with an oscilloscope and you trace out the circuit while it's cycling that one faulty instruction.
Right.
Right? Or that one failing memory address or whatever. Right?
Right.
So, yeah. So anyway, we are really miles away from what you wanted to interview me about.
No, I think you've actually intuitively gone the direction of that I like to. But yeah, no, let's keep going through your journey.
Fine. Okay, fine. Well, do you want me to keep it at this level of detail and pace?
Sure, that's great. I'll go as long as you'll stay on. So,
well, we may be here for a few hours before we get to Lutz.
Yeah. Well, we'll have to do a part 2 if that's the case.
Well, actually, you can just carve. If we go too long, make it into 2 episodes or whatever.
Right.
Okay. So I did basically. So this started off as a summer job, but I ended up doing again after school work for this researcher, and so for about 2 years I was doing programming in the evening and building a disk drive controller and learning about the internals of PDP-8s, and that continued up until around 1976, so 2 years later, when that researcher changed from one hospital to another, and I followed him, and he said, what are we going to get? Are we going to get a PDP-8, or do you want to try one of these newfangled PDP-11s? And the PDP-8 was what I knew, and I said, well, I really know this one, but if you don't mind me taking time coming up to speed, let's go for a PDP-11.
Right.
Now, the PDP-11s had been around all through this time, but we couldn't, the doctor couldn't afford them. But now he had more research money, and so we got probably one of the first PDP-11 34s. So there were 4 or 5 models before this, and I won't go through the models, but they basically all execute almost the same instruction set. That is, there were different ways that they implemented the execution of the instruction set, and there were little nooks and corners in the instruction set where, because the ISA wasn't nailed down in concrete, you could get situations where a PDP-10 and a PDP-20, PDP-1110 or a PDP-1120 might execute an instruction that you would never normally write, right? But they would execute it differently. And so there were, a set of, different little tests you could do to figure out what machine you were running on.
Ah, I see.
Right. Okay. So, I think the earliest machines were just strict pile of gates type, decode the instruction and run it type stuff.
Mm-hmm.
By the time you get to the PDP-1134, it was a microcoded machine.
Okay.
Okay. So microcoded machines, and this is actually worth doing because this actually moves into a lot of other stuff. In that time frame, so from the late 60s onwards, there was a chip made initially by Fairchild called the 74181, and it is a 4-bit ALU with an internal 4-bit carry chain and carry in and carry out that let you put multiple of these 74181s side by side, right, to build arbitrary width arithmetic paths, right? And so for a PDP-8, there would be 3 of those chips side by side. For a PDP-11, there'd be 4 of them. And when eventually you get to the VAX 11780, which was DEC's first 32-bit computer, there's 8 of them, right? And so that's an ALU-only chip, but it also introduced special... so basically the 7400 series is mostly just building block chips, but there were a few very function-specific stuff. And so one of the things the 74181 ALU chip did was it didn't just generate carry in and carry out. It also had additional pins called generate and propagate.
Okay.
And generate and propagate are a fast analysis of the operands and the carry logic that bypasses the ripple process of rippling carry from one bit to the next.
Right.
It doesn't create an answer, but it in broadside, so very, very quickly can say if the 4-bit operation that chip is doing, if there's a carry in, it always will generate a carry out.
Ah, okay.
Sorry, regardless of the carry in,
right,
it'll always generate a carry out. So that's a generate. Right, so the generate pin of a 181 says, I know I'm going to generate a carry no matter what the carry in is. Right? The propagate signal coming out of a 74181 says, I will propagate a carry if there's a carry in.
Gotcha.
So that means outside of the 181, you can look at the signal you're providing to the carry in pin and the propagate signal and the generate signal that are calculated independent of the actual calculating the add or the subtract.
Right.
And you can pre-calculate or concurrently calculate the carry into the next 4 bits. Right?
Right.
So that lets you get a very fast carry in across 4 bits.
Right.
If you're putting 4 of those chips together, Fairchild designed a part called the 74182, and it had generate and propagate inputs that would come from all 4 of those chips and look at the carry in at the very beginning of a 16-bit thing, and it would generate a generate and propagate across all 16 bits.
Oh, okay. Right.
Very fast. Right? And so if you're, depending on the size of the processor you're building, you built a tree of these 182 chips, right? And so the 181s are doing the arithmetic, having to deal with actual carry propagates, carry ripples through the arithmetic path.
Right.
But you've got these generate propagate signals that are predicting, right, ahead of stuff.
Right.
So the domain of adding 2 numbers in 2's complement, or 1's complement for that matter, has been an area of research for decades.
Right.
And so if you go look at how do you add 2 numbers together, right, there's the simplest stuff at one end, which is you add the first 2 bits and you look at is it a carry the 1 problem?
Right.
Right. Right. And then you do the next 2 bits and then the next 2 bits and the next 1 bit, 2 operands, right?
Right.
And you keep doing that, right?
Right.
Then you have things like the generate propagate tree. But that isn't the fastest way to go.
Right.
There are other things. There's things called carry select adders, where you calculate both answers concurrently, one with carry in and one without carry in. And then you use the carry in signal to drive a mux to select between the 2 answers.
Right.
And you still use those generate propagate 182s to control a carry select data.
Right.
It has the overhead of muxes. It has the bonus that it's faster.
Right. I love examples, even if they are, not the ultimate optimization of something like the generate and propagate, because they make it abundantly clear that a big part of performance improvements is understanding what dependencies do exist and what things are false dependencies, right? And if you can look at something that's a false dependency and say, oh, we can actually do this at the same time, then sometimes you get the incremental speed up, sometimes you get, really big performance changes.
Right, yeah. So, in fact, as your adders get bigger, this generate propagate stuff actually improves performance on an exponential curve, right? Because you end up, if you were doing a 64-bit add, you're doing it in the same time that it takes a 5-bit add to occur.
Right.
Right. Because most of the stuff that takes time is now it's the generate propagates, because all the other stuff runs sort of concurrently.
Right.
Right. So we actually see some of this in DSP for why FPGAs dominate the very high end of the DSP marketplace. So I'm going to take a little side trip to expand on this thought. So one of the most common DSP functions that is insanely computationally heavy is digital filters. But they're simple, right? They're simple. You take a vector of coefficients and a vector of data, and you multiply each element of the data vector by the appropriate coefficient, right? And the set of coefficients will basically, and so it's actually that the term is sum of products. You may have heard that term. So the product is the multiplier of the coefficient by the operand repeated by n different elements.
Right.
So if you look at a DSP chip, right, anything from Texas Instruments or Analog Devices for that matter, right, those DSP chips have vector instructions where you point at the coefficient array and the data array, which might have come in from an A to D converter, or it might be a scan line from a video image or whatever. And then it, as fast as possible, fetches two operands at once, multiplies them together, and adds the result. So if you start with two 16-bit operands, you multiply them together, the worst case is a 32-bit result.
Right.
If you add two of those together, the worst case thing is 33 bits. Right? If both of those 32-bit numbers were near max, right, you'll end up with a 33-bit result. You need one extra bit if you're only adding two of them. If you add four of them, you need one more bit. If you have 8 of them, you need one more bit, 16, 32. So depending how many elements you're adding together, you need more bits in that accumulator. Right. So now we look at where does it make sense of how big should that accumulator be? And that, in fact, will limit how big the array can be before you have to do something special. Right. So if you're going to do, let's say, add 4,096, multiply 4,096 operands with 4,096 coefficients, right? If that's what you want to do, then your accumulator needs 12 extra bits. Right. So it'll be 32 bits plus 12. And if you're doing floating point as a way to avoid doing that, right, of needing extra bits, then you have to consider whether you're really doing the arithmetic you think you're doing, because you're going to start throwing away all your low order bits, because whether you add them or multiply them or whatever, they're going to get pushed out by all the other arithmetic that you're doing. Right. So there's a balance of when does... Well, first of all, floating point typically is massively slower than integer. Right? Typically. Except for some chips where they just throw an insane amount of hardware at it and they bring floating point not up to the performance of pure integer, but maybe a factor of 3 to 5 times slower.
Right.
It depends on the processor and how much silicon you want to throw at it. Okay, so that's how DSP is done in a DSP processor for a common task, which is what I've described to you has a name. It's called an FIR filter. Right? So, and it's finite impulse response. And I could go into what that means, but it's irrelevant to this discussion.
All right.
What's important is that if I have let's say I have a data vector of 1,024 elements, right? Then I've got to do 1,024 multiplies and 1,023 adds.
Right.
Right? And so that's going to take me, even if I overlap the adds over the multiplies, and the multiply accumulate section always does that, right? You're up for approximately 1,024 system cycles.
Right.
Plus you've got to fetch 2,048 things out of memory.
Right.
Right? And so if you look at DSP chips, you will find that different regions of memory can be accessed concurrently. Right? So in something like a TMS 320 something, you might find that the on-chip memory, which might be a quarter of a megabyte, is broken up into 4 blocks, right, of 128K, and the processor can fetch 4 operands in one clock. Right. So that lets them, have 2 pointers, both fetching one from the operand list, one from the coefficient list, pushing them through the multiplier, into the adder, into the accumulator, and then keep doing that. It still takes order n, right? It takes 1,024 cycles. How would you ever improve that? And then along comes FPGAs. And FPGAs say, I've got 1,024 operations. I can do the first multiply and accumulate and the second multiply accumulate. I can do them concurrently and store the result if I can fetch enough operands. Right? And some of the DSP chips will do that too. Some of them have dual multiply accumulators. Right? But there's a limit to how many they have. Right? In an FPGA, there are FPGAs that have tens of thousands of multiply accumulators in them. That's current technology. The early stuff, they were measured in tens to low hundreds. But even so, let's say you've got a chip. Let's say you've got a chip that has 1,024 multipliers. Right? You can fetch, if you set things up right, maybe you can fetch all 1,024 coefficients all at once. And you can take your data that was coming from an A to D converter, have that going through a shift register that is word wide. And when all 1,024 words are in exactly the right place, fire off all 1,024 multipliers all at once. And you get 1,024 multipliers in one cycle. And you combine the results of 2 of those multipliers. So you actually don't care about the intermediate adds. Right? You don't have to store them. All you want is to know the results. So you have 512 adders that combine 2 different multipliers, which on a DSP chip would have been 2 consecutive multipliers. On the FPGA, it's a pair of concurrent multipliers, and you get 512 additions, which all happen in one cycle. You follow those 512 adders by 128 adders, followed by 64, 32, whatever. You end up with about 11 stages deep. Right? And so in 11 clock cycles, plus the 1 clock to do all the multiplies, you have the result of 1024 multiplies and 1024 adds, you have it in 11 clocks.
Right.
But each of those stages was only used for 1/11th of that time.
Right.
So take that data that was in that shift register and shift it one position, and now do another 1024 multiplies.
Right.
And have those results marching behind down through that adder tree.
Right.
Right.
You've got a pipeline
and so
situation going.
Now you've got something that took 1024 clocks.
Right.
Right. To fill the pipeline. So that's your startup latency.
Right.
But after you've paid that latency of 1024 clocks, which is a millisecond,
right,
you're now delivering a result every single clock.
Every cycle, yep.
So here's how an FIR filter works. You set up the coefficients to be a pattern that you're looking for, right? And you set up your data is streaming, and it's somewhere in this data is the pattern I want to find.
Right.
And now in a single clock cycle, whereas a DSP chip, it will take 1024 clocks before you can shift the shift register once. In the FPGA, you shift it every clock.
Right.
So the FPGA is running 1024 times faster than a DSP chip. And they both had the same startup latency, right?
Right.
They both couldn't start until you had your first 1024 data items. But the DSP chip won't, after it's shifted everything one position, it's another 1024 cycles until you get an answer.
Right.
The FPGA, it's one clock because they were coming down through the pipeline of adders.
So could the DSP chip could, in theory, also have 1024 multiply and then the add tree as well, right? It's just that most of the time they do not, and there's no, you couldn't control expanding it or contracting it as you needed, right?
You couldn't make it application specific, and it wouldn't be able to do anything else.
Right.
And it would instead of being the relatively cheap price that a DSP chip is, which might be in the $10 to $12, it might end up being like these high-end FPGAs, which are $2,000 to $3,000.
Right.
But for the FPGA, if what you really needed was that 1024 position FIR filter running at 100 megahertz, delivering a new result every 10 nanoseconds, right? So every 10 nanoseconds, it does 1024 multiplies and 1023 adds and delivers a result, right? That FPGA might cost you a few $1,000s. Right? Maybe. I don't know what the current prices are. Maybe it's a few $100s. It doesn't matter, right? The point is, no amount of banging on the side of your DSP chip will hit that performance target. Right? And the cool thing for the FPGA is, if you only need to do that until the radar says, I've now found the target, now switch from search mode to tracking mode, right? That's load a different bit stream and now track the target that you found with that FIR filter, right? Or now go into an image recognition algorithm, or whatever else. By the way, there is of course a two-dimensional version. So what I've described is a single-dimensional FIR. There are two-dimensional FIRs which get applied to images and do things like edge sharpening and blurring or feature recognition, etc. Right? The FIR filter is a workhorse of the DSP domain, which covers image, audio, radar, and almost everywhere where you're dealing with real world signals, right? Other than on and off, right? There are DSP algorithms often involved. Right. So, an FIR filter can also, boost the bass and trim the treble or whatever else. I mean, it's a general purpose algorithm, and it's functionally easy to implement, but it is computationally heavy. Right? And again, it's the example of looking at a DSP chip, which is inherently sequential, and the FPGA, which offers but doesn't enforce a parallel solution. Right? If you're working only with DSP chips, that parallel tree-based solution just never occurs to you because it's not part of the architecture. For the FPGA, it takes a while to reshape into thinking in terms of the extreme parallelism that FPGAs are capable of, right? But that's the reason that, high-end communication systems, satellite communications, wireless, G3, next generation TV distribution, FPGAs are used in all of these systems because they can implement these highly parallel solutions, and you don't have to commit to a custom chip, which when they go and change the standard will now all be unusable.
Right. Absolutely.
Right?
I've definitely heard that.
For the FPGA, yeah. When the FPGA, when the algorithm changes or the standard changes, the FPGA says, well, okay, send me a new bit stream.
Right, exactly.
Right. So, an interesting view of, understanding your algorithms, right, is really important. When you want to do optimization, I generally say look at your algorithms first before you start looking at boosting the clock speed or throwing more chips at it or putting a water cooler on it and overclocking it. Right. Before you do those things, go look at your algorithm and see if there's a better way.
Right.
In a very, I won't say cynical, but it's cynical. I've been of the general impression that when someone uses floating point for an algorithm, they don't understand their algorithm. Right? Floating point is the crutch for not knowing what's going on in your data. Right? If you really understand what your data looks like and how you're manipulating it at each stage, for most applications, not all, but for most applications, there is a pure integer solution, or at worst, an integer solution with an invisible binary point somewhere. Right. Breaking it into the integer part and the fractional part of a binary number. Right. And I hope you noticed I was very explicit that it's not the decimal point.
Right.
I get angry when people refer to that as a decimal point when they're looking at binary or octal or hex data. The term that, and by the way, all of this comes from when I worked at AMD, where I was designing these types of chips. That is the bit slice products and the RISC CPUs. I resolved that by giving it my generic name is the radix point. So rather than the decimal point, for whatever radix you're working, whether it's decimal, hex, octal, or binary, that dot is the radix point. Then I get less frustrated and angry.
Well, to encourage you to continue listening to the podcast after this episode, I'll try to ensure that other guests as well adhere to that practice. But you mentioned AMD, right? And this is kind of, I guess, fast forwarding a few years from where we last left you. But I think you joined AMD in 1985. Is that right?
That's correct. So that's 5. That's about, we've jumped over about 6 or 7 years there.
Okay.
And that's fine. We could do it later or not do it. It doesn't matter. You did ask on the notes that you gave me that, how much planning was there? And so let me at least talk a little bit about that, because
please do.
One of the things I guess I would say permeates my approach to stuff is planning. Right. I mean, I ended up in a department as a manager of product planning at AMD,
Right.
and then later at Xilinx. But my planning stuff dated back 6 years before I ended up at AMD, right? So I'm going to jump us back to that 74181.
Okay.
I'm going to jump over everything else that's relevant, but I'm going to come back to the 181. That approach to building the ALU as a slice of 4 bits of what is a larger data path, that ended up getting a name called bit slice.
Okay.
And its origin was, and I don't remember who had it first, but it was either Intel had a 2-bit slice ALU, or Monolithic Memories had a 4-bit slice ALU, right? And these were more than the 74181. They added the register file. So rather than having the 2 operands that feed into the ALU being in external chips, right, the bit slice processors, which were basically a 181 with a register file, right, there was a 2-bit version called the 3002, I think, from Intel, and then there was a 6701, I think, was the part number from Monolithic Memories. Okay, and it was a 4-bit slice, and the ALUs in both of them were not as good as the 74181.
Okay.
Right, but they did do add, subtract, and or XOR, shift left and shift right by 1 bit. And actually the shift left and shift right meant you needed additional communication bits, right? So if you're only doing add and subtract, you just need a carry borrow line. Right. But for shift in the shift left, you can use the carry chain. But for shift right, you need something that's pointing the other way.
Right.
Right. Okay. So, that added an additional across the ALU type control signal. So MMI wasn't particularly successful with their bit slice ALUs. I haven't ever heard of a system that was built with them. But one of the managers at MMI moved, and this would have been probably in the mid-70s, moved from MMI to AMD, and at AMD the 2901 was born. And the 2901 was far and away the most successful bit slice processor. And it was a 4-bit ALU that was more functional than the 6701. It had a better register file. It had generate and propagate lines that I don't think the 6701 had. So you could actually use these bit slice chips from AMD with the Fairchild 182 chip, right, and build and take advantage of that generate propagate logic.
Right.
And so lots of computers, both mini computers and mainframe computers, were built with 2901s. So for instance, the Data General answer to the DEC VAX. So when DEC went from the PDP-11 to the VAX 11780, which happened in 1978, I believe, right? That was still using 141s. Data General had a competitive machine called the MV8000, and it used 2901s from AMD. And then you started seeing 2901s in mainframe computers from pretty much everyone except IBM, right? And mini computers, so later models of PDP-11s probably used 2901s. And there were a lot of other companies that looked at the success of Data General and DEC and were lesser players, but still building CPUs. And then in the early 80s through to the late 80s, there was a new range of computers built by a bunch of startups which were called mini supercomputers. So they weren't quite the Cray or CDC, 6700 type, real super duper computers, but they were machines that were bigger than the biggest mini computers, but they could handle workloads and compute that typically used RISC type instruction sets and bit slice ALUs.
Right.
Yeah. So anyway, how did I get down on that path? Don't remember. Oh, other than to say, the style of building stuff got more integrated.
Mm-hmm.
So anyway, I was aware of all this stuff in the late 70s.
Right.
And so by this time, I'd already designed my first chip. I hadn't mentioned that. I designed my first chip in 1972 when I was 12 years old.
Okay.
At that time frame, Fairchild and National Semiconductor actually had factories in Australia, in Melbourne.
Mm-hmm.
Only an hour's travel by public transport for a 12-year-old. And they were test and packaging.
Okay.
Right. So the chips came in as wafers, already fully processed. They were then tested, diced, and packaged.
Mm-hmm.
Right. Some going to export and some feeding into the minuscule Australian electronics industry.
Right.
So I went and visited just as I went off to Honeywell's timeshare building, I went off to Fairchild, right, and asked for a tour. And so I got a tour by one of the sales engineers through the manufacturing floor. And it wasn't a particularly big facility. They basically, there was probably less than 100 people working there, right? Mm-hmm. But I got to see all that. And, I asked about, so how do these, chips get designed? And the guy says, well, some people in America in the product, and this is Fairchild, right?
Yeah.
They look at the features that people want, or the salespeople tell them these are the features that customers are asking for, and then they plan the products. And this guy really didn't understand how that then turned into a product.
Right.
So then, stuff happens and the chips end up here, and here the exciting stuff happens. We cut them up, we test them, and we package them, right?
Right.
So he skipped over the whole, design the chip part, because he really didn't have any handle on that. And he just talked about what was locally there. I said, so what if I had an idea for a chip, because I keep wanting this function, but it isn't in the 7400 catalog? And he says, I have no idea.
Yeah.
I said, well, if I wrote a data sheet for the chip, right, would you send it to those people? And he said, sure. And so I wrote a data sheet.
Yep.
And laid out the pinout and the logic function and the timing table. So basically all the stuff, and I typed it up on a typewriter. I didn't have a word processor back then, right? And I gave him this 4 or 5 sheet data sheet for a chip that would have something that I was using often, which was an RS latch, which was a pair of cross-coupled NAND gates, which is used, among other things, to debounce switches.
Right.
Right, so that you get nice, clean transitions. I said, you've got all these pins. You could have 4 of these in one chip rather than me going through all of these 7400 NAND chips, right? You could have 4 of these circuits in one package. Mm-hmm. That chip is still built today, and it's called the 74LS279. So that was my first product planning experience.
Did you get any attribution in this process at all?
Never. But I claim, and there's no one still alive to deny it. I claim I designed the 74LS279.
Well, that is probably not something many 12-year-olds can say.
Yeah, well, and or believe at this point.
Right.
It doesn't matter. The point was, it got me into understanding right, the process of, you need a data sheet, you need to have thought through the functionality, you need to make sure it doesn't need more pins than the package has, right, et cetera, et cetera. Okay, so late 70s, I'm now programming PDP-11s. I've got a real job actually working in Fortran in a company. We're going to skip over all of that unless you want to go back at it later. And I'm looking at what are people using for building processors? And the answer is they're using AMD 2901s. Right? And so I start learning about bit slice. Right? I mean, I already had a handle on it from using the 181s, but now I'm looking at what replaced them. Right? And I'm looking at how it changed. I said, damn it, I want to end up somewhere near that. So the only company I want to work for is AMD. Right. So I want to work for AMD. I figured there was no way I'd get to work on bit slice directly. So my goal was, how do I at least get to make coffee for those guys? Right. That was my plan. Get to make coffee for the guys who worked in the bit slice department so I could talk with them. Right. From Australia, the closest I could get to AMD in Australia was AMD had a distributor. So AMD didn't have any physical presence in Australia at all, but there was a distributor called R&D Electronics, and they distributed AMD's parts. They also handled Intersil, Monolithic Memories, Zilog, and a bunch of other companies. So in Australia, the common thing is since none of the silicon companies had a presence in the country, because Fairchild and Nat Semi's packaging division had decamped years ago due to some political silliness, right? So Australia had no silicon industry whatsoever. But there was a bunch of distributor companies. These days, you'd talk about DigiKey and Mauser, etc., right? So these are much smaller versions of that for the much smaller Australian market, and they represented multiple product lines, typically trying to avoid conflicts of interest, right? So if you look at the product line from AMD, Mono Memories, Intersil, Varro, and Zilog, there's almost no overlap between them, right? And so they were presented to customers. If a customer says, I want this, we would look through our catalog of parts, right, and say, well, we have a solution for you and it uses these MMI parts or whatever. So anyway, in Australia, all of these distributor type companies were just basically sales and shipping organizations and a little bit of marketing. The equivalent in the US, though, they typically had something called a applications engineer. Right? In fact, if you look at a company like AMD, it actually has two categories of application engineers, internal and external. So the internal application engineers answer the telephones, solve problems, write the data sheets, probably write the application notes, and they take the calls from the other application engineers who are out in the field, who are called field application engineers. Right? Big surprise. So a field application engineer who has a problem with a specific customer would work with the customer to refine the problem description, right, whatever that might be, and then approach the applications department inside the company to have someone take ownership of it and either resolve it using the internal resources, which might include going off and talking to the chip designer. Right? Depends what was, what level of skill is needed to resolve the issue. So in the US, the distributors all had application engineers, right, who are external. Not all of them worked for AMD, right, or Intersil or whatever, right? They worked for the distributor. So you had two categories of external FAEs. You have field application engineers who are distributor FAEs, second-class citizens, and then you have first-class citizens who worked in AMD's sales offices spread across the country, right? Who primarily only ever talked to the really big customers. Right? For all the little customers, they sent them off to the distributors. Right? But once a year, AMD held their international sales conference and FAE conference, and they upgraded the distributor FAEs, and they were invited as well. And so they had a conference that would run for a week, right? And they had all the distributor FAEs, all the company external FAEs, and all the internal application engineers, all in a huge conference facility, in AMD's case, usually in Hawaii. And then factory people from the engineering department would make presentations about what is in the pipeline and what to look out for in terms of opportunities. Plus marketing and sales people would say, here's the products we already have, right? Here's how you go about, here's the types of customers you look for, here's the products you offer them, right? So it's a sales and engineering conference.
Right.
AMD had them once a year. That included external FAEs that work for distributors. In Australia, none of the distributors had any FAEs. So I approached Australia's AMD distributor, a company called R&D Electronics, and said, have you considered having an application engineer across all your products? And the owner of the company said, we've been thinking about it, but we didn't know who we'd go get.
Right.
And I put my hand up and said, I'll do it. I would love to be Australia's first field application engineer.
Right.
And so that happened at the end of 1979. I joined as an FAE, and while my primary goal was eventually to make coffee for the BitSlice people in California, the first thing was to become competent as an application engineer. And I did it across all of that company's product lines that it represented.
Right.
So I didn't just become an AMD FAE, I became an MMI FAE, and I became an Intersil FAE, and several other companies. The MMI FAE position turned out to be, in the short term, the most useful, because I got to see PALs before they got released. And so I was basically training people how to use PALs when they first became available from MMI. Right? Which was a wonderful experience. Right? Wonderful. But I also became, an FAE for AMD, and so within my first year of joining this company, they sent me to America.
Awesome.
Right? And I got to attend the application, the sales and application conference. And I got to meet, it wasn't my expectation, but I actually got to meet some of the people who were the actual chip designers in the BitSlice group.
Right.
And had interesting discussions. So I stayed with that company for about 3 years, attending conferences on an annual basis and building up my contacts at AMD and at MMI and at Intersil and various other companies, right? And I had a load of fun in Australia, talking to lots of people, lots of different engineering teams, all with different problems. So I got to see a very broad range of electronic design and different levels of competence of teams and whatever. Eventually I left that company because I wanted to actually do some engineering.
Right.
And I joined a pair of small companies, one after the other, both of which had serious management problems. Okay. And didn't last very long.
And these were Australian companies?
Yeah. These are Australian companies with under 20 employees doing primarily S100-based computer stuff, both designing boards and building systems and selling accounting software and business software and that sort of stuff. That didn't last more than a year. So it was basically 2 companies, 6 months each, and it was like, this is not for me.
Right.
Then all through that period, I'd also been a lecturer at one of the local universities, teaching final year system design. So 4th year EE degree students, I was teaching system design and balancing trade-offs and writing low-level code and a little bit of DSP and a little bit of making Ethernet work, etc., etc.
Mm-hmm.
So after the 2 small companies that really didn't suit me, I asked the university if I could become a full-time lecturer.
Mm-hmm.
And so I hadn't lost sight of wanting to work in BitSlice, but I didn't feel I was quite ready to make the jump. And I didn't actually have any opportunity for that. So I took on a role in Australia. The job title was senior lecturer. The US equivalent would be associate professor.
Okay.
That is responsible for course creation
Mm-hmm.
and syllabus and examination and evaluation, etc. So it was reasonably autonomous, but not professor level, high status.
Right. Fair enough.
Right. But I basically created a new digital course that was fun to teach. Unfortunately, when I moved from being a part-time lecturer where I was just teaching 2 subjects a week, so all the time that I was being an application engineer, I was also taking off half a day per week to teach at that university.
Okay.
So they already knew me.
Right.
And that company that I was working for was incredibly nice to let me have half a day off a week to teach at the university. They figured I'm training their next generation of customers. Right? Because guess what? The data books that I handed out for them to do their assignments, the data books were AMD and MMI and Intersil.
Right.
So it was, there was clearly, some linkage there. Anyway, the politics when I became a full-time member of staff was unbearable. The trivial politics between the various academics just drove me nuts.
Right.
And so about 6 months in, I sent my resume off to the head of applications at AMD and said, could you please pass this on to someone in the applications department, right, to see if I could become an AMD internal applications engineer.
Mm.
So that was my path. I figured with my credentials, having been a field application engineer in Australia and having multiple years of them seeing me, that it would be pretty easy.
Right.
Unfortunately, it took 3 or 4 resumes being sent because the guy kept throwing them in the trash, which was very sad. But eventually, instead of trashing it, he gave my resume to the head of the BitSlice group.
Oh wow, that was
the product planning group for BitSlice.
Okay.
And so he called me. So long distance phone call.
Mm-hmm.
He called me and interviewed me for about an hour.
Okay.
And I told him about how I had, with a bunch of friends of mine, so we've skipped over all of this, but starting in 1980 when I became an employee at this distributor company,
Mm-hmm.
I also bought parts at a discount. And I bought a pile of BitSlice processor chips and all the stuff that goes around it. And a bunch of friends and I had actually built a 32-bit mainframe.
Oh, wow.
Right? So we actually had some very interesting stuff. It's not for this discussion, but as a do I know anything about BitSlice? The answer was, I have a 32-bit mainframe that my friends and I designed and built, and it's 4 times the performance of DEC's VAX.
Right. I'm sure the interview went pretty well after that.
Yeah, it did. It went really well. And he said, we'll probably get back to you. And later that day, I got a call from HR with a job offer. And unfortunately, I just started that semester. I said, so all of this is great. I didn't even care how much they were offering me. I wasn't going to be making coffee for this group. I would actually become part of that group as my entrance into AMD.
Right.
So I just started the semester. I said, I'm going to have to delay by 6 months. Otherwise, I'm going to be stranding, right, a whole class of students.
Right.
And they agreed to it. I half regret it, but I don't have any guilt of having stranded students, which if I'd instead jumped at it and stranded those students, I'd probably have felt bad about it for at least a while.
Right.
But instead, I taught that semester and then packed up everything I owned and headed off to America. And so by this time, I'm now late 20s, and I joined AMD not as a junior in that department, but one of two managers. So there was a guy in charge of that department, and then under him he had slots for two managers, and then under those two managers were then the rest of the department.
Okay.
And so he brought me in as AMD's term was a section manager. And so I was a section manager in the Programmable Processors division.
Okay.
Right, responsible for, I thought, bit slice products. But it turns out, nuh-uh. It turns out the department had a secret project that was unannounced to the outside world, which was a RISC CPU. And so they had just finished a round of next generation bit slice parts, and rather than doing another round of it, they decided, for whatever reason, that RISC made more sense as the next thing that their skill set, right? So the rest of AMD was busy copying Intel instruction sets, right? Whereas this group, the bit slice group, was designing instruction sets. Right? And the RISC CPU would be designing an instruction set as well, right? So that's where it belonged, at least initially.
Right.
And so they brought me in because of my bit slice experience of actually having built stuff. So bit slice in general, microcoded processors, is not RISC at all. It's CISC, right? You're building interpreters that are below, that implement the assembler language.
Right. So would the bit slice components, would they fit into the CISC processors as like a target essentially for the microcode inside of the larger system?
Very much.
Okay.
Yeah. Right. So pretty much all of these bit slice parts were implementing CISC CPUs.
Okay.
Right. So the bit slice parts are pretty much inherently not driven by assembler, they're driven by microassembler code or microcode, right? And so you have, an instruction that might be 64 bits wide or wider that's controlling all these different microcoded chips concurrently. In fact, the machine that we built in Australia had a microcode instruction that was 128 bits wide. Right, and so it was controlling a lot of stuff concurrently, which is part of what made it fast. Right. But it was still cycling around an interpreter loop, interpreting an upper level assembler.
Right.
So anyway, I was coming in to work in the RISC group, but I'm the guy that doesn't believe in RISC. Right. I have immersed myself for at least the last 5 or 6 years on CISC type stuff. And this RISC group was built from the bit slice group, which was also of CISC architecture origin.
Right.
So the manager, when he brought me in, said, I want you to spend a few weeks going through all of their documents and analyzing it and tell me if we're heading in the wrong direction. right? Because I'm coming in as a very solid CISC type viewpoint and experience of actually building CISC CPUs. Is this RISC thing really better?
Right.
So I worked on it for 2 weeks, went through all the documentation they had, all their estimates of timing, the instruction flows, whatever else. And at the end I said to the boss, this is insane, right? It's crazy to keep me doing this task. Put me on the RISC team.
Yeah.
This is the future.
Wow.
Right? And so basically I became one of the co-architects. I mean, in total there were 8 engineers who architected the 29,000, right? And everybody contributed. So I wasn't like a lead architect or anything. I was one of a team. Although I had 3 other engineers under me, which, by the way, I'd never had reports. And I'm not a great people person.
You could have fooled me.
Well, I'm not sure I did my best, but I'm much better at pushing gates than pushing people.
Fair enough.
So I did my best, and I really enjoyed working. We really worked more as colleagues than as manager and underlings, right? So there was, like, for instance, myself and one of my underlings wrote the cross assembler for the 29,000, right? And I worked with another person on various other tasks, right? So there was a lot of real work that, as a manager, I still got my hands totally dirty along with everybody else in the team.
Right. In that 2-week window, though, that you were talking about, where you kind of became convinced, if you will, I've read quite a bit about the kind of like RISC versus CISC academic debates more in that time period. What was it that you saw in those 2 weeks that made you a convert, if you will?
So one of the things that I carried from my Australian project is when I convinced a bunch of friends to help me build this machine, which was all done as wire wrap, was I said, I think we need some guiding ideas that are forward-looking, right? Rather than working with what we have, let's predict where something is going and design for that target, right? And I said, among the things that we've seen is that chips get more and more complex, but the other thing is that the cost of memory keeps dropping and the size of memory keeps going up. Let's use as a guiding principle for this CISC machine that we were building, let's use as a guiding principle that memory is free. So wherever we're making decisions where memory might be involved, don't treat it as a scarce resource. Treat it as something that's free. So the fact that the microcode memory was 128 bits wide, not an issue. The fact that it was 1/4 megaword deep, when most companies were looking at like a kiloword or 2 kilowords, we were doing 256K deep microcode memory. Totally outside of any norm.
Right.
But it let us do things, right? In terms of the way we cracked instructions in the interpretive loop, we could just have separate routines for groups of instructions that are very, very similar, but would have an overhead to sort out the minor differences. We could just, with that much microcode, we just have unique microcode for each one and avoid a branch and a compare, right, as part of the decode loop,
right,
as an example. Late in the project, we virtualized it.
Okay.
So we had demand paged microcode, right? Because memory's free. The register file was 4,096 registers, right? And the instructions that the microcode engine could execute could fetch any 2 registers, perform an ALU op, and write back to any 3rd register every clock. right? Because memory's free.
Right.
I mean, it wasn't, and so we didn't implement everything.
Right.
But we used that as a guiding principle.
Mm-hmm.
So the memory is free. I brought that with me when I started looking at the AMD project. And the number one thing that people pointed at for RISC is because the instructions are so simple, right, you're going to have so many more of them.
Right.
And memory's expensive. And I said, no, it isn't.
Right.
Memory's free. Right? Memory's free. And so that's no longer an issue for RISC, right? Because in time, right, that memory that you're worried about, how much it costs, it's not going to matter.
Right.
Right? The performance is going to matter.
Mm-hmm.
Right? How fast can I fetch instructions? And with RISC, there were two things. One was that memory is free thing got rid of one of the anti-RISC sort of arguments.
Right.
But the other one, I didn't see it directly. It was an education that I got from one of the guys that was... Okay, so by the way, that team of architects on 29,000 at AMD,
mm-hmm.
of the 8 people, 5 of them were fresh out of college.
Oh, wow.
Right? So 5 of them were new grads who hadn't worked anywhere prior to AMD.
Mm-hmm.
And the rest of them, there was me, a guy from National Semiconductor, and a guy from IBM. The IBM guy had worked on IBM's RISC processor that eventually became PowerPC.
Mm-hmm.
Right? So one of the guys who was fresh out of college educated me on compiler optimizations. Mm-hmm. And he was very strong on how, because all the instead of having microcode where everything is set in concrete for how each instruction is executed, on a RISC CPU you can take a step up the a layer out on the onion to the next layer out. So you're not trying to execute single assembler instructions, you're trying to do some algorithmic piece.
Right.
And there are optimizations you can do. Right. The best example is, let's say instruction A has to store to a register, mm-hmm. and instruction B has to fetch from the same register.
Right.
And they happen one after the other. Well, in a RISC CPU, maybe that's a direct path, and you're not touching the register file at all. There's an intermediate register that's otherwise invisible, mm-hmm. right? But lets you over 2 clocks do something that would have taken 3 or 4 clocks and blown away a register along the way,
right.
which, could have been used, for holding a useful coefficient or something.
Mm-hmm.
So it was that for the RISC CPUs, there were lots of opportunities for optimizations in the compiler,
right.
that would help you do a better job with the limited resources that the RISC CPU provides. And so it really mitigated more of it allowed finer grain optimizations. Mm-hmm. And I really liked that. So it was the finer grain optimizations. It was the argument that memory is expensive. We had benchmarks. We had that same guy had written a GCC backend for the sketched out architecture. The architecture that AMD had for 29,000 was not yet set in concrete. The broad strokes were done, but the detailed instruction set hadn't been done. Mm-hmm. We knew what types of instructions there'd be. We knew the approximate layout of the bit fields in the instructions. Some of that surprisingly is important, in that you want to be able to take instruction bits and route them directly to where they're needed,
right.
like maybe controlling a mux or directly going into an ALU to select which ALU function, rather than having to be decoded and then generate a control word, which is a different bit pattern.
Right.
You want to avoid that. And so some of that is literally the artistry of figuring out the bits of an opcode. Like, so the 29000 is a 32-bit instruction, 8 bits of opcode, and 3 8-bit fields. Right? And sometimes 2 of them are joined to create a 16-bit field. But the 8-bit instruction field, certain of those bits are routed directly to the ALU. Certain bits go off other places. But suffice to say, there's a lot of stuff there where you avoid having to put a mux in a critical path because you just lay out the bit fields. So that was stuff I knew about. And in fact, I was one that did the detailed design. Right? The instruction set had already been figured out by other people, but they hadn't yet figured out how does that get mapped to the opcodes. Right? And so one of the tasks, I said, it's a tedious job, but I'm willing to do it. Right? And so I actually figured out the exact bit patterns for every instruction and optimized them so that it would work. In fact, even things like there's fetch 2 registers and write back to the third. Do you really want those 3 fields to be in some arbitrary combination of 3 8-bit fields, or is there an optimal one? And the answer is, well, if I'm going to have 16-bit constants and I want to write them to a register, then maybe the 16-bit constant should be the bottom 16 bits, and the write-back register should be the next 8 bits, and the opcode should be the top 8 bits. Right? As an example. The simplest version of this, considering where bits are in the instruction that I've experienced at least is, implementing a RISC-V CPU. RISC-V, one of the nice things about it is arguments are always in the same place. There's lots of different instruction formats, but if there's RS1 and RS2, right? They're always at the same place in the instruction if they're present. And once you actually try to implement the logic, right, for a CPU, you understand how important that is. But, if you haven't done that before, then it's not, if all you've ever done is programmed in assembler, that's opaque to you. And that, what you're describing, literally the 29000 does that too, right? So there are instructions that only have a destination register. There are instructions that have a destination and 1 operand and a short immediate, right, of 8 bits. And then there's instructions which fetch 2 registers and write back to a third. And because there is a place in the data path where you have to choose between a register being fetched and that short immediate, or 2 registers being fetched and the long immediate, right, the 16-bit immediate, those mean there are muxes somewhere. Right, that have to decide, am I taking the bits from the instruction, or am I taking the bits that the instruction is indexing into the register file, and there's a register file access that is pipelined, so I won't actually get that register for another clock, right? So there's a bunch of juggling there, right? And it wasn't like something I'd knocked out in an afternoon, right? I probably spent 2 or 3 weeks designing the bit patterns for the instruction set, right? So anyway, there was just a bunch of things that I saw in what the 29000 was capable of doing, and what I knew it was competing against in CISC would always require multiple instructions, and that interpretation process was blocking optimizations that were open to well-written compilers. Right? And it may surprise some of the listeners that it is, if you know what's going on behind the scenes, RISC won 100%. Right? And you say, but x86 dominates the market. x86 on the package dominates the market. Inside, both AMD and Intel's x86s are RISC CPUs. Right? And they all have a an on-the-fly translation engine and caches that translate the x86's instructions into RISC operations. AMD calls them ROPS, R-O-P-S, and they then go into the ROPS cache, right? And the actual compute engine is executing from the ROPS cache, running RISC instructions, right? So and some of those are doing optimizations on the fly as well. Although again, there are opportunities in the compiler to help things along. Right. Okay. Where would you like me to talk next?
Well, one of the other things about the, I don't know if it was the 29,000 or another chip that you worked on, but we also briefly, I think in the past, talked about register windows. Were those on the 29,000?
Yeah, that was on the 29,000. So
okay,
it's interesting. I've wondered. So the comparison is, so there were two processors that used a rolling window of registers that the execution stream is busy modifying. And one way, the term we used, and you'll have to forgive me a little bit because we're talking 37 years ago, right? So it's been a little while since I worked on this. Someone commented to me that as you get older, you talk less about the great things that you'll do in the future and more about the great things you've done in the past. So I'm clearly in that in the older category, and some of it the memory fades because it's back far enough. But so one of the things that was part of the 29,000's architecture well before a lot of work had been done before I arrived. A lot of work. And one of them was that that there'd be this register window. And so basically what a register window is it says that all the registers live in memory, right? And there were processors before the 29,000 that did that. Among them was the Texas Instruments 9900, which dates from the 70s, except it really had all the registers sitting in memory. Right? So kind of slow, right? Right. The register file in the 29,000, we referred to it as a stack cache. So it's and there is, for the purpose of this discussion, we'll say there's 128 registers. There isn't. There's actually 192. It was originally 256 and we ran out of room. Right. So originally, because we had 8-bit fields, right, it was intended to index into the register file with 256 registers. Well, it turns out the chip design guys couldn't build the chip because there were too many registers, and so something had to go, and we ended up throwing away 64 registers. And so we have a lower half of 128 registers and the upper half of 64, which used to be 128, right? So there's a negative optimization because we ran out of silicon, right? And that then propagated to every member of the family afterwards. Okay, so the 120. So let's talk about half of the register file that was still there, right? It was 128 registers. Nominally, the stack pointer is a pointer somewhere into those 128 registers. And all the registers above that pointer position are parts of the stack that haven't been touched yet or are stale from previous execution. And the stuff below the stack pointer is active stack frames that we plan to look at as we unroll the stack. Okay, so the register file, 128 registers, is like a barrel. Right? You have a pointer that says, here's where I am in the 128 registers. there's a marker that says this is the first of the valid registers, and so there, up to the stack pointer, is the top of stack with n registers. And then you have from there to, you wrap around to that same boundary pointer, which are the registers that you could use because the cache is sitting there. You just haven't dug deep enough in your subroutines yet.
Right.
Okay. So when you want to do a subroutine call, you compare the current stack pointer, bottom 7 bits, to the boundary register, bottom 7 bits, and you say, do I have enough room to allocate the registers that I need for this function, right? So the compiler optimization already knows I'm passing 3 parameters plus a return address plus a frame pointer or something, and they're all going to get pushed on the stack, and then we're going to jump off to the subroutine. So I need 7 registers. Are 7 registers available above the current stack pointer, right? And you look at it, says, yes, there are. So you just update the frame register, you update the stack pointer, you put your parameters into the appropriate places in the stack cache, and you go to your subroutine, and it can then do indirect or offset references to the new stack pointer to get its parameters off the stack. And if it wants to call another routine, it does the same calling convention.
Right.
Eventually, if you just keep digging down, right, deeper and deeper into a subroutine call tree, eventually there won't be enough registers.
Right.
The registers that are furthest away, which are right at that boundary register, but looking at it from going backwards, those are the ones you're not going to want to look at for a long time until you unwind the stack. So you flush them out to real memory.
Right.
Okay? That's called a spill, right? And you just move the reference pointer, right, to however many registers you threw away. And now magically you've got more stack, right? So the cost of doing a spill, which is when you're digging down through the subroutine tree, right, is the cost of writing the registers out and updating the pointer. And you have a choice when you design your compiler or when you design the ABI for the processor of whether the spill is only as many as you need or spill everything, not a good choice, or maybe spill half, right? And I don't remember, we certainly didn't spill only as many as you need, and we certainly didn't spill everything. I think the default was you just always spill half, right?
Gotcha.
So you spilled 64 registers out to memory, and then you continued executing code. Now, eventually you start executing return instructions, and eventually the frame pointer is pointing back before the reference pointer, which says the registers you want aren't in the cache, right?
Right.
And so now you do a fill, right? So you're unwinding the stack call, so now you do a fill, and the fill is bring in 64 registers.
Right.
Right? And so nominally, the stack pointer is always in the middle with 64 registers behind it and 64 registers after it. And so, again, we ran, and when I say we, I mean not me, we ran benchmarks and code traces, right, to figure out that whatever it was that the spill and fill quantities were, they basically meant that a very high percentage of subroutine calls triggered neither a spill or a fill. Right? So you had something like 95, 97% of subroutine calls didn't trigger a spill or a fill. So the efficiency was outstanding. Right? So you always had the top of stack, right, which had all your subroutine parameters or return values or whatever, are just always available in the fastest memory the chip has, right? The register file.
And so that's a an optimization versus like some other register window strategies, but just to like compare to not using register windows, right? If you have registers that you need to preserve across a subroutine call, you have to have a function prologue or prelude where you're going to push it onto the stack. And so one of the things you're saving is all of those operations where you're manually pushing and popping things to stack, right?
In fact, if you look at x86 code, right, or ARM code for that matter, because ARM has a similar problem, you'll see, particularly for things that might end up being interrupt service routines, right, is they end up having to flush all the registers, right, out to memory because you need a working set. On the 29000, you say, my interrupt service routine needs X registers. Can I just move the pointer and give it X of its own registers? And when we're done, we'll return them all. So absolute register numbers, they don't exist in 29000 code. They're all, what is the offset from the top of stack? And the top of stack is always on chip, not out somewhere in main memory, right? It's somewhere within those 128 registers. Right.
I did some analysis of I basically heard about register windows from learning about Spark, and I was looking at x86 and ARM and now RISC-V, and I was curious why none of these newer, if you will, right? I mean, some of these trace back to before, but why they don't use register windows. And I did a bunch of reading. I ended up writing a blog post that kind of like went through some of the trade-offs. But I know I had briefly mentioned to you seeing a comment about Spark register windows were perhaps not implemented quite as efficiently. Do you think that contributed to register windows not being included in subsequent architectures?
I don't think so. I think that the Spark decision, so Spark also has register windows that spill and fill. The difference between it and 29000 is the pool of registers is smaller and the allocation size is fixed. So it's when you enter a subroutine, the movement of the frame register is always by the same amount. Whereas for 29000, it's optimized on a per function basis. So if you only need 3 registers, you only consume 3 registers. Whereas Spark always consumes 12 or something. I don't remember the number, but whatever it is, because it always consumes a fixed amount, it's always over allocating, which means it's spilling and filling far more often than 29000. And I would guess that the reason is because of the layout of their instruction didn't give them the flexibility of having a field as part of the call instruction that said, here's how many registers I need to allocate.
Right.
So in the 29000, part of that subroutine call is the frame increment. Right. So, and that was because of the way that those bit fields were laid out. Was we had an 8-bit immediate field that you weren't needing for the subroutine call. Right. Or actually, it was how was it done? It was actually not the immediate field. It was the destination register field. Right. The one that was always available, and that left you with a 16-bit relative offset for how far away the function could be. So you could be up to 64K words of offset, right? Which was split 32K before and after the current PC value. And if you needed more than that, there was a different call instruction that said call indirect through a register. Right, which would have a 32-bit absolute address or a 32-bit offset from the current program counter.
Right. Makes
sense. So I suspect it was just a function of how the bits were laid out. And, there was also an overhead that it required an extra 8-bit adder in a somewhat critical register access path.
Mm-hmm.
Right? So, it wasn't without its own costs in the silicon implementation.
Right.
Yeah.
Right. That makes sense.
Yeah.
From a maybe as a kind of wrap up of where we've gone so far, and we haven't even gotten to Xilinx and FPGAs and everything. So I am absolutely going to have you back. But from your time at AMD, maybe specifically on the 29000 or other work that you did there, was there any other kind of like lessons or takeaways that you had, both from the perspective of things we've been talking about, of specific to processor architecture, but also just general organizational takeaways as well?
I have a career worth of organizational takeaways. Be really careful picking your boss, and when you do, make sure that what you're doing matches your boss's goals. Right? You need to be on their team and working to meet whatever their goals are. So that's real important. Understand what the hot buttons are of whoever is managing you, and make sure you don't do anything to shoot yourself in the foot.
Right.
I did that a few too many times. If you have the ability of getting a boss who really understands, I guess I've had this attitude that the function of a manager / boss is to protect the people below from the crap above. Right? So you have people above your boss's level who are busy jerking chains and changing schedules and doing things that would really upset what the team is trying to get done on what is probably a tight schedule. And so a good boss insulates the worker bees from the politics that are really shouldn't affect them. Right. And I've had bosses both who do that well and don't do it well at all. And it really affects you. I have a fairly complex, I guess, architectural observation, not mine. This is when I joined AMD's. So AMD's product planning, and I know it's in your question list, which is how different was AMD product planning from Xilinx, and there's an Australian term which I think we should propagate to America. It's like chalk and cheese.
Okay.
Right? They might look the same, right? Sort of, just a piece of chalk, piece of cheese. Like, take a bite, you'll see there's a difference, right? So anyway, the Australian term, here it's like apples and oranges, or something in pickup trucks or whatever. But the Australian term it's like chalk and cheese. It's just really different. So anyway, one of the things that AMD had was actually a product planning department. So the group I was part of, the processor products group, was one of several teams. There was, so our team was like 8 or 9 people total, including its section manager. I think product planning was like maybe 90 engineers.
Oh, wow.
And because AMD back in those days had a very broad range of proprietary products, right? They've sold all of that stuff off, but there was a PLD group that did PALs. There was a networking group that built Ethernet chips and communication chips and RS-485 stuff. There was a group that was doing video graphics chips. These are all 1980s type stuff, right? So not like PC type stuff, right? The PC wasn't really much on the horizon yet. It was basically monochrome monitors at that point, right? So there was a graphics group, There was a group doing disk controllers. There was a group doing microcontrollers, sort of 8051 type stuff. There was a memories group. I used to joke with other people in my group that the memory group's product planners had the easiest job in the company. They needed to come in once a year, take a data sheet, mark it up by doubling all the numbers, throw it back into the thing, and then go away for a year.
Right.
So anyway, there was about 90 engineers in product planning. Almost, not all, but almost all of them had industry experience building systems. Okay? That is almost unique to AMD. Right?
Okay.
I think Intel has at least something similar in that their processor architects, I think, have all worked on building motherboards. Right? Whereas AMD's, like the guys that ended up, for instance, in AMD's product planning group for graphics chips, had worked somewhere else on graphic systems. The disk controller guys had worked for some big disk manufacturer, right? So the engineers in product planning at AMD all had, not all, almost all had actual domain-specific industry experience.
Right.
Usually when I'm being cynical, hard to believe I could be cynical. Usually when I'm being cynical about just chip companies in general, my common comment, and it's every time I see something stupid in some chip that I didn't design, right, is these people couldn't design a board with 2 chips to save their life, right? And I will say that I've seen that as true of most chip designers, right? They go through the Carver-Mead, playing with rectangles path, right? And lambdas and whatever else. But actually building a system with 50 chips on a board and making the clock tree work and the race conditions work and the logic worked first time, whatever. Actual system design, most chip designers have made it through college out with a degree saying, I know how to run Allegro or Cadence tools or whatever, and I can design you a $1 billion chip. But give them a an 8-bit microprocessor chip and a LED and an EEPROM and ask them to put it together, they have no idea which end of the soldering iron to pick up. Right. So that was certainly a difference with AMD's product planners. At Xilinx, which is where I worked later, I was the first product planner, so I couldn't point to other people who didn't have that. But certainly the IC designers there, they were great IC designers, but the common thing you see, and not just at AMD, I saw it at AMD, at Xilinx, I saw it at MMI, and I've seen it in data sheets from other companies, is chip designers will have a problem and they'll push it out to the pins and say, the chip is perfect. Right? And they've left something that's now pushed out to the pins, right, which may be impossible to deal with. Right? I've certainly seen chips where literally there's stuff that's happening on the pins where there's no external way to make the chip work reliably. Right? Very sad. The products end up failing terribly because everyone who tries to build it either has to put enormous amounts of effort to work around the problem, or they don't spot the problem and they go into production where 20% of the boards don't work because the chip has this inherent bug and no amount of patch wires is going to make it suddenly better. Right.
Interesting. Okay. Yeah, I think the analog that we have in the software engineering world is you always want to work with product managers who used to be engineers. That's frequently something we look for. Yeah. So, Yeah, it's been a
Right.
good rule to live by.
Yeah. So anyway, the reason I talked about the fact that there was about 90 engineers in product planning at AMD was there was a guiding light for overall for AMD in that time frame, which was that AMD was the products were building blocks, right? So all of the bit slice was the building blocks to build arbitrary size computers, from mini computers, mini mainframes to mainframes.
Mm-hmm.
The graphics chips were building block chips. So there were things like chips that did texturing, chips that did the line rendering, right? There were basically building blocks in different combinations might let you build different types of graphic systems. And that permeated all of AMD's products in the 70s and the 80s. The guiding light within AMD's product planning group, which was, I was educated about this from an early time of joining, was that the term was mechanisms, not policies. So create the mechanisms to let an end customer build the system he wants, right? Don't do something in the chip that sets a policy which he or she has no way of working around, or the chip is just not a good fit because you've already decided on a policy that might not match what they need for their system, right?
Right.
So when you look at all of those types of products, that was kind of a guiding light. I mean, there were some products where, if it was a 2400 baud modem chip, AMD made a 2400 baud modem chip, then guess what? That was policy from beginning to end, because there was a spec for this is what a 24 kilobit modem chip does. These are the frequencies it has to transmit and receive on. These are the signal levels. Here's where the serial comes in and out on RS-232 levels. Build a chip, right?
Mm-hmm.
Right. So there were some chips where where policy was set, by specs. But in general, it was that if you're doing building blocks, build general functionality and flexibility, right? And leave it to the end user to figure out which combination of building blocks is the best way to build his castle.
Right. Awesome. Well, like I said, we're definitely going to have you back, but this was an incredibly enjoyable conversation for me.
Too.
I hope you
Me
enjoyed.
Too.
Awesome.
Yep.
Awesome. That's great to hear. Well, Philip, thank you for joining us, and we'll look forward to next time having you on again.
Yeah. Okay, Dan. Thank you very, very much.